I am Monica Bertus, and my science fair project was on airfoil efficiency. I wanted to know how angle of attack affected airfoil efficiency. An airfoil is the shape of a wing. I used an undercambered airfoil, a flat-bottomed airfoil, and a symmetrical airfoil. Angle of attack is the angle at which the airfoil faces the air it is moving through. This is some of my research. Airfoil efficiency is the amount of lift an airfoil produces over how much drag it produces. Lift is the force that makes airplanes go up. Drag is the force that opposes motion through a fluid. There are two explanations for why lift works. Bernoulli's principle, where the air on top of the airfoil has to go farther and therefore faster than the air on the bottom of the airfoil. This creates higher pressure under the bottom of the airfoil, pushing the airfoil up. Newton's third law is the other explanation. The air is bent around the airfoil, forcing the air downward and the airfoil upward. I believe that all the airfoils will generate more lift as the angle of attack increases, and it will start to decrease at the stalling point when there isn't enough laminar or smooth airflow. I believe the symmetrical airfoil will not produce any lift at 0 degrees AOA because it is not shaped to direct any air downward, nor does it make the airflow faster over the top without the angle of attack. I believe that the flat-bottomed airfoil will create more lift than the symmetrical airfoil, but not as much as the undercambered airfoil, as the undercambered airfoil's tail points downward on its own. I also believe that all the airfoils will create more drag as the absolute value of the angle of attack increases, because more air particles will collide with the airfoil. The symmetrical airfoil will create the least drag as it is the most aerodynamic, and the undercambered airfoil will create the most drag. Therefore, I also believe that the graph for the airfoil efficiency will look similar to the graph for lift, except before the angle of attack of 0, the airfoil efficiency will go down like drag. I also believe that the flat-bottomed airfoil will be the most efficient because while I don't predict it to create the most lift, I don't believe it will create high amounts of drag either. My independent variable was the angle of attack, and my measured variables were lift and drag in grams. For my experiment, I needed a 3D printed symmetric, flat-bottomed, and undercambered airfoil, a leaf blower, a stand to hold up the airfoil at different angles of attack. This is what I used for drag, and this is what I used for lift. I used a spring scale to measure drag and a scale to measure lift. This apparatus measures lift, or the force that makes airplanes go up. When the leaf blower is turned on, it makes the air flow over the airfoil, which then produces lift. The scale measures the difference in the weight before I turn on the leaf blower and after I turn on the leaf blower, or how much lift is produced. This is the apparatus I use to measure drag, or the force that resists motion. The air moves from the leaf blower and hits the airfoil, which makes the airfoil move backwards. The sticks are connected at the bottom to a string, so when this moves backward, the sticks move forward, and the string pulls out the spring scale, and the spring scale measures how many grams of force is created. I explained how I measured lift and drag, but I should note that I was able to measure lift from -15 to 25 degrees by 5 degrees because I was able to move the airfoil on its own, whereas for the drag apparatus, I had to drill holes, and if I had measured it every 5 degrees, I'm uncertain whether the apparatus would have held up. These are some of my data tables for lift and drag. This is my graph for how much lift is produced at each angle of attack. As you can see, the amount of lift increases as the angle of attack increases until the stalling point, where they all start to decrease. Throughout all of the angle of attacks, the most lift was produced by the undercambered airfoil, followed by the flat-bottomed airfoil, until a part of it where the symmetrical airfoil was higher. My results showed the farther the angle of attack was from zero, the more drag was produced. The undercambered airfoil produced the most drag, followed by the symmetrical airfoil and the flat-bottomed airfoil. As you can see, airfoil efficiency went down like drag and went up and down like lift. The flat-bottomed airfoil was the most efficient throughout most of the angles. The symmetrical airfoil, though, created the most airfoil efficiency of all the airfoils at about 10 degrees. The undercambered airfoil was the least efficient. Another thing to note is how similar the symmetrical airfoil looks on both sides of zero. I tested how angle of attack affects airfoil efficiency. I believe that airfoil efficiency would go down as the angle of attack reached zero, and then follow the curve I predicted lift to take. I believe that the flat-bottomed airfoil would be the most efficient, the symmetrical airfoil to create the least amount of drag, and the undercambered airfoil to create the most lift. I was right about how the angle of attack would affect airfoil efficiency, and that the undercambered airfoil would create the most lift, but the symmetrical airfoil had the best efficiency overall, and the flat-bottomed airfoil created the least amount of drag. While it may seem bad that the undercambered airfoils produced a greater amount of drag and symmetrical airfoils a large amount of negative lift, these airfoils are great for specific uses. The undercambered airfoil can create large quantities of lift at low speeds, so it is useful during liftoff and for airplanes that have to take off from short runways. A symmetrical airfoil is the same right side up as upside down, which is why it creates negative lift. Therefore, planes that need to be able to flip upside down rely on symmetrical airfoils. Different airfoils are designed for different speeds, so I'm unsure if the efficiency of the airfoils would differ at different speeds. If I did this experiment again, I could test different speeds, which materials best for airfoils, or how different airfoils on different parts of a wing would affect efficiency. These are a few of my sources I used for my research. And this is the sources I used to get the images throughout my slideshow.